Today we're diving into one of the most fascinating tissues in the human body. It may look simple, just a tiny red liquid when you cut your finger, but blood is incredibly complex and vital. It's not only the transfer system for oxygen and nutrients, but also the body's communication network, waste removal service, and defense force. Think of it as the ultimate multitasker. Just one drop contains millions of cells, proteins, and chemical signals, all working together to keep you alive. Over the next couple of slides, we'll explore what blood is made of, how it functions, and what happens when the system breaks down. By the end, you'll be able to see why blood is truly the river of life. When we think about blood, we can't separate it from the larger circulatory system. The heart is the pump, the vessels are the highways, and the blood is the transport medium. Together, they form an interconnected network that keeps us alive. Blood isn't just moving oxygen, it's carrying nutrients from the digestive system, ferrying carbon dioxide to the lungs, delivering waste to the kidneys and liver, and also helping regulate body temperature. On top of that, it's patrolled by immune cells, consistently and constantly on guard against infections. So blood is more than just a red liquid, it's multitasking tissue that touches every system in our body. Blood is actually a connective tissue, just a very unusual one. Instead of a solid matrix like bone or cartilage, its extracellular matrix is liquid. Inside the plasma flows deformed elements, which are cells and cell fragments like red blood cells, white blood cells, and platelets. Adults carry about 4 to 6 liters depending on sex, which is roughly 7 to 8% of the body weight. And it's thick, about 5 times more viscous than water. That thickness is key to its ability to transport nutrients and gases efficiently. If you spin blood in a centrifuge, you'll see the two main layers, the plasma layer and the formed elements. Plasma makes up about 55% and contains water, proteins, hormones, nutrients, and wastes. Formed elements include the red blood cells, white blood cells, and platelets, which make up the other 45. That simple split tells you a lot. Plasma is the transport fluid, and the cells are the workforce. Of that 55%, plasma is 90% water, and water provides the medium for transport. The other 10%, the dissolved solutes, are the business end. Proteins like albumins help maintain osmotic balance, globulins act as carriers or antibodies, and clotting proteins keep us from bleeding out. And add in the ions, hormones, amino acids, and metabolic waste, and plasma becomes a dynamic soup of chemistry that supports the body. Albumins act like the sponges keeping water balanced between blood and tissues. Globulins split into alpha, beta, and gamma types. Beta transports lipids, gamma transports antibodies, and essential to immunity. And of course, clotting proteins like fibrinogen ensure blood can actually seal wounds. This means plasma just doesn't carry dissolved substances, it actively regulates physiology and protects us. Red blood cells are the workhorse of the transport system. Each one is packed with hemoglobin, which is a protein designed to carry oxygen and carbon dioxide. They lack a nucleus and organelles, which maximize space for hemoglobin, but also means they can't repair themselves. That's why their lifespan is roughly 120 days. Imagine about 5 million of these per cubic millimeter of blood constantly replaced by the stem cells in our bone marrow. This production is tightly controlled by hormones, the hormone erythropoietin, or EPO, which acts like the body's red blood cell thermostat. All blood cells, not just the red ones, come from the same source, hematopoietic stem cells in the bone marrow. These cells are remarkable because they can keep dividing for life, ensuring continuous supply of new blood cells. Depending on signals, they can branch off into red blood cells, white blood cells, or platelets. This makes the marrow one of the busiest factories in the body. Immature red blood cells are called erythroblasts. As they mature, they fill with hemoglobin and jettison their nucleus and organelles, a permanent commitment to gas transport. After about 4 months in circulation, they wear out and are removed by macrophages in the liver and spleen. The body is very efficient. Iron and amino acids are recycled, while the heme group is converted into bilirubin and excreted through the digestive tract. Here's where EPO really matters. Kidney cells monitor oxygen levels in the blood. If oxygen is low, say like in high altitudes or after blood loss, they release EPO, which stimulates bone marrow to make more red blood cells. This feedback loop keeps oxygen delivery in balance. But there's also complications. People with kidney disease may not produce enough EPO, leading to anemia. On the flip side, some athletes abuse synthetic EPO to boost performance, which thickens the blood and forces the heart to work dangerously hard. Now let's shift from oxygen delivery to defense. White blood cells are far fewer in number than red blood cells, about 7,000 per cubic millimeter of blood. But they're critical for immunity. They act like mobile guardians, protecting against infections and coordinating inflammation. Unlike red blood cells, they can split out of the bloodstream and patrol tissues directly. Their number can rise rapidly during infections, showing just how responsive the immune system can actually be. Granular white blood cells are the first responders. Neutrophils make up a majority of about roughly 60%, and they're the first ones to rush to an infection site, gobbling up bacteria. Eosinophils are less common but specialized. They actually attack large parasites like worms and also help tone down allergic reactions. Basophils, though rare, release histamine, which fuels inflammation and allergic responses. So while they look similar under the microscope, each type has its own specialty in defense and defending the body. Now, agranular leukocytes like monocytes and lymphocytes. Monocytes can leave the blood and become macrophages, big eaters that clean up debris and pathogens. Lymphocytes are central in adaptive immunity. B cells produce antibodies while T cells attack infected or abnormal cells directly. Together they create memory so that the body can respond faster to future infections. Without them, vaccines would not actually work. Platelets aren't full cells at all. They're actually fragments of larger cells called megakaryocytes. But they are vital because they kick off clotting when vessels is damaged. They don't just stick together, they also release chemical signals that recruit more platelets and trigger repair processes. Without them, even small cuts would become life-threatening. Stopping blood loss is actually a three-step process. First, vascular spasms narrow the vessel to limit flow. Second, platelets stick to damage and form a plug. Finally, the clotting cascade creates a stable blood clot. It's impressive. Within minutes, liquid blood transforms into a gel-like seal. Small vessels can seal themselves with spasms alone, with larger ones relying heavily on clotting. Here's where the chemistry comes alive. Platelets release prothrombin activator, which converts prothrombin into thrombin. Thrombin then converts fibrinogen into fibrin strands. These strands weave together, trapping platelets and red blood cells to form a blood clot. Think of it like throwing a net across a breach in a dam. Once stabilized, the clot contracts and tightens to secure the seal. Sometimes the clotting system doesn't actually work the way it should. In hemophilia, for example, a person is missing one of the crucial blood clotting factors, most often factor VIII. Even minor injuries can lead to dangerous bleeding. Thanks to biotechnology, factor VIII can now be made through genetic engineering and given to patients. On the other hand, some common medications like aspirin, ibuprofen, and naproxen interfere with the platelet's function. This is useful in preventing blood clots in certain patients, but can also increase bleeding risk. When we move into transfusions, compatibility is everything. A person's blood type is determined by the antigens on their red blood cells. The ABO system and the Rh factor are the most important. If the wrong blood type is given, the recipient's immune system may attack those foreign cells, leading to severe and potentially fatal reactions. So blood typing is not just a detail, it's life or death matter. Antigens are simply proteins that the immune system can recognize as self or non-self. If your red blood cells carry an antigen that's unfamiliar with the recipient, their body will treat those cells like invaders. This is why cross-matching before transfusion is critical. It ensures that donating blood won't trigger the recipient's immune defense. Antibodies on the flip side of the equation. These proteins circulate in plasma and target specific antigens. For example, if you have type A blood, your plasma carries anti-B antibodies. That means if you receive type B blood, your antibodies will attack those cells. The key point is that it's not the donor's antibodies that cause the trouble, it's the recipient's antibodies acting and reacting to the donor's red blood cells. The ABO system boils down to which antigens are present. Type A has A antigens, type B has B antigens, while type AB has both and type O has neither. Their plasma contained antibodies against the antigen, so they don't have. This is why type O is a universal donor. It has no antigens to trigger a reaction. And type AB is a universal recipient, since it has no antibodies. Understanding this system is the foundation of safe transfusion practices. When it comes to transfusions, the rule is simple. The recipients must not receive red blood cells that carry antigens their antibodies will attack. For example, someone with type A blood has anti-B antibodies, so they can safely receive type A or O blood, but never A or AB. Type B can only take B or O. Type AB can receive any type, making them universal recipients. Type O, on the other hand, can only receive type O, but can donate to anyone. This logic has saved countless lives in transfusion medicine. The Rh factor is another antigen that is present on about 85% of the people. If you're Rh positive, your cells carry it. If you're Rh negative, they don't, and your immune system can actually form anti-Rh antibodies if exposed to the Rh positive blood. This doesn't usually matter day to day, but it becomes very important during pregnancy. Here's where things get serious. An anti-Rh negative mother carrying an Rh positive fetus can develop antibodies against the baby's red blood cells. The first pregnancy is usually safe, but in later pregnancies, those maternal antibodies can cross the placenta and attack the fetus's red blood cells, causing hemolytic disease of newborns. This condition can actually be life-threatening. Thankfully, we can prevent this giving the mother an injection of RhoGAM, which is anti-Rh antibodies during pregnancy, and after delivery prevents her immune system from producing its own antibodies. In essence, it tricks her immune system into ignoring the Rh antigen. This is one of medicine's best examples of preventing rather than actual treatment. Before any transfusion, two things happen: blood typing and cross-matching. Blood typing determines the ABO and Rh groups. Cross-matching goes further. It mixes donor cells with recipient's plasma to check for agglutination or clumping. No clumping means that the match is safe. This double check system dramatically reduces the risk of transfusion reactions. Blood donation is one of the simplest, most powerful ways to save a life. Donors go through screenings of health, travel history, and potential risks, plus testing for viruses like HIV, hepatitis, and Zika. The actual process takes about 20 minutes and carries no risk of infection to the donor. The body replaces plasma volumes within an hour, and red blood cells are replenished in a few weeks. Blood can be used whole or separated into plasma, plaque red blood cells, and platelets, allowing one donation to help multiple patients. So why look for alternatives? Donor blood has limits. It can carry infectious risks, may not be the right type, and can't be stored indefinitely. Researchers are exploring two main substitutes. The first is modified hemoglobin solutions, though hemoglobin must be packed carefully to avoid toxicity. The second is perfluorocarbon, which can carry even more oxygen than blood, but only temporarily. These substitutes can bridge emergencies, but aren't yet a full replacement for human blood. Blood can also be the target of infections. Mononucleosis, or the kissing disease, is caused by the Epstein-Barr virus and infects lymphocytes, leaving patients fatigued and achy. Septicemia, or blood poisoning, is more dangerous. It is bacterial infections in the bloodstream, often following wounds, burns, or urinary tract infections. It spreads fast and can be life-threatening, require immediate antibiotics. These highlight how vulnerable blood is to systemic infections. Anemia is the most common blood disorder, defined as a reduced oxygen carrying capacity. It can result from few red blood cells or insufficient hemoglobin. Iron deficiency anemia is widespread and linked to poor diet or absorption. Hemolytic anemia comes from blood loss. Pernicious anemia results from vitamin B12 deficiency. Hemolytic anemia is due to the premature red blood cell destruction. And in kidney failure, low EPO leads to fewer red blood cells being made. Different causes, same outcome: fatigue, weakness, and reduced oxygen delivery. Leukemia is a cancer of the white blood cells. Cells proliferate uncontrollably and crowd out normal blood components. It may be acute or chronic, and treatment includes chemotherapy, radiation, and bone marrow transplants. Multiple myeloma, which is another type of cancer, affects plasma cells in the marrow, weakening bone and reducing healthy blood cells production. Both disorders remind us that when cells regulation in the marrow breaks down, the consequences ripple throughout the body. Thrombocytopenia is a disorder where platelets numbers drops too low. Without enough platelets, clotting becomes an inefficiency leading to unusual bruising, nosebleeds, or prolonged bleeding even from minor injuries. Causes range from viral infections to certain medications to leukemia or radiation exposure. It highlights how fragile the balance is. Too many clots can block vessels. Too few platelets leave us vulnerable to bleeding.